Hello, my name's Rob Lindburn. I'm the section lead for industrial process microbiology here at Camden BRI. One of the areas that my group commonly asked to advise on is process recommendations, minimum process requirements for various different types of food product. And there are quite a lot of provision these days in terms of safe harbor processes for this type of product. So for example, for chilled products, there's a 70 degrees C for 2-minute process with a Z value of 7.5, which is used to target Listeria monocytogenes in these types of product. And that's been long established since the late 80s and has been tested against a whole range of different chilled products. There are various different other processes that are applied to things like milk, for example, or ambient pH controlled products, all of which have various different process requirements. And these are very easy to use, standard processes which will cover most types of product and make it very easy, therefore, to establish what your minimum criteria should be and to help you to validate those. But there are some situations whereby you might want to consider what the inactivation characteristics of microorganisms are in your particular product to help you to achieve a safer or a more cost-effective process in some cases. So some of these instances are where you have a product which has particular characteristics, for example, low water activity or high total solids. Say you have high levels of protein, high levels of carbohydrate, or high levels of sugar in the product. These characteristics can be quite protective towards microorganisms. So maybe in those cases, you need to have slightly more severe process in order to ensure that you're achieving a safe food at the end of the process. Similarly, you may be struggling to achieve your quality parameters. So say, for example, there's sensory quality your product is you're struggling to achieve with the standard off-the-shelf process. And it could be that process may be overkill for your particular product. So in that instance, it's possible to do some work to establish whether you need to have, for example, a 70 degrees C for 2 minutes process, or could you get away with something less severe while still achieving the same level of safety? So that's the second scenario. The third scenario would be where you have a process failure and say, for example, there's an outbreak of a pathogen or indeed a spoilage incident within your product. And it's been determined through your root cause analysis that the process is responsible, i.e. it's coming through the heat process as opposed to being something post-process contamination. In that instance, you'll obviously need to establish how to remedy this situation. And again, it'll come back to establishing what the minimum process criteria should be for your actual product. And finally, there are certain circumstances where low temperature processes are required. So for example, sous vide processing of meats and things like that. Now this is a bit of a contentious area. So it's felt that the sort of standard process inactivation kinetics still hold at low temperature. But it's appreciated from the data there's a lot more variability around low temperature. So if you do need to process at low temperature, you'll need quite a robust amount of data to support your worst case for your process. So those are the four main sort of areas where you might need to optimize your process. Now, how do we go about that? So the first thing would be to check published literature and see if there's any credible published literature out there which better matches the physical characteristics of your product. If so, then those parameters can be applied directly to your product, potentially. If there isn't any guidance out there in published literature, or not a sufficient amount, then it comes down to an experimental determination of the minimum process requirements for pasteurization. In these cases, it will come to an inoculated study. So you would need to inoculate samples of the product with the known pathogen, heat them across a range of temperatures and establish D values. This is the inactivation rate at a particular temperature for each temperature. And that would allow us to model then the inactivation over a range of temperature and use that model to establish and predict the minimum times required to achieve your log reduction target. And what that can do is obviously optimize your process to make sure that it's safe, giving you peace of mind that you've done the due diligence required to ensure that your process is safe, also giving your customers a lot more reassurance that you are applying a process which is tailored to your actual product. Similarly, if you find that you can reduce the severity of the process, then there's a lot of cost reduction in terms of energy costs potentially to be had there, and indeed time costs in certain circumstances. And then finally, in terms of spoilage, if you're responding to a spoilage incident, then you're looking at waste reduction. So all of the product that you would have had to throw out at great cost and at great expense to your environmental credentials would be reduced significantly. So these are the sort of the benefits of optimizing your process. Obviously, in reality, it's quite a complex area. So you require quite a lot of expertise in the area in order to make sure that the experimental design is correct, ensuring that any process you're applying is actually going to achieve your aims. And we can certainly help in that area. We have many years of experience of helping our customers to determine such experimental procedures. So if you do need any help in that area, please feel free to contact us and we'll be happy to help you. Thank you.